In this session, we will learn some alternative representations of LP parameters, which are often used in speech analysis instead of LP coefficients. LPC is frequently used for transmitting spectral envelope information, and as such, it has to be tolerant of transmission errors. Transmission of the filter coefficients directly is undesirable, since they are very sensitive to errors. In other words, a very small error can distort the whole spectrum or worse. A small error might make the prediction filter unstable. Linear prediction parameters, alpha k, are sensitive to the small change like quantization error and interpolation error in coding, and the LP filter, Hz, is not easy to be stable. There are many alternative representations, such as log area ratios LAR, line spectral pairs LSP, and reflection coefficients. Of this, especially LSP parameters have gained popularity, since it ensures stability of the predictor, and the spectral errors are local for small coefficients deviations. In the cascade sound tube model, the sound channel is simulated as a series of cascades of lossless sound tubes with different lengths and cross-sectional areas. The reflection coefficient stands for the amount of reflection of sound waves at the boundary of each sound tube section. The reflection coefficients are also called partial correlation coefficients, named PARCORS. There is a recurrent relationship between PARCORS and LP coefficients. Assume that LP coefficients alpha g are given, then we can work backwards through the Levin-Dubin recursion to get PARCORS parameters Ki. Conversely, the prediction coefficients can be gotten from PARCORS parameters. Assume that PARCORS parameters Ki, I equals 1, 2, and P are given, then we can escape the computation of Ki in Levin-Dubin recursion to obtain LP coefficients alpha g. By taking the roots of predictor polynomial, the resonance peaks can be estimated. The prediction error filter Az can be equivalently expressed by a set of rules Zk, which is important for format estimation, where each root can be expressed as a z-plane or s-plane. In s-plane, the parameters omega k determines the frequency of the format. Delta k determines the bandwidth of the format. Linear spectrum pair LSP is also a deduction parameters of linear prediction coefficients. LSP parameters have very good quantization characteristics and interpolation characteristics. So, they have been widely used in speech coding research. The prediction inverse filter, Az, is all zeros filter with all zeros Zk inside the unit circle. We can get another filter, A hat Z, with a form of reciprocal polynomial with inverse zeros. Based on these two filters, we can form the symmetric polynomial Pz and the anti-symmetric polynomial Qz. Considering the all-pass system LZ, PZ has zeros for LZ equals -1, and QZ has zeros for LZ -1. Zeros of PZ and QZ fall on unit circle and are interleaved with each other. The set of omega k are called linear spectral frequencies, LSF, which are in ascending order. Stability of LP filter HZ guaranteed by quantizing LSF parameters. Zeros of PZ and QZ appear in pairs and reflect the spectral characteristic of the signal. So they are called line spectral pair coefficients. Line spectral pair parameters have some properties. The first one, PZ corresponds to a lossless tube, open at the lips and open at the glottis. And second, QZ corresponds to a lossless tube, open at the lips and closed at the glottis. The third, all the roots of PZ and QZ are on the unit circle. The fourth, if P is an even integer, then PZ has a root at z equals +1 and QZ has a root at z equals -1. The fifth, a necessary and sufficient condition for the absolute value ki smaller than 1 is that the roots of PZ and QZ alternate on the unit circle. The sixth, the LSP frequencies get close together when roots of AZ are close to the unit circle. Number 7, the roots of PZ are approximately equal to the format frequencies. In speech analysis, our goal is to represent speech by a small number of slowly varying parameters, reflecting the changing nature of the shape of the vocal cavities and the motion of the vocal cords. The theory of linear prediction provides an accurate representation of speech in terms of a few as low as 12 parameters specified once every 10 or 20 milliseconds. Consider now an application such as digital speech coding. In speech coding, we are interested in transmitting speech over a digital communication channel at low bitrate. The theory of linear prediction allows us to determine exactly what is predictable in the signal and remove that information from the speech signal before transmission on the digital channel. One typical scheme of LP-based speech codec is shown in the figure. At the encoder, the input speech is processed frame by frame and firstly passes through pre-processing model. The pitch detector and LPC analysis are carried out to obtain pitch cycles. LPC parameters and residual parameters, all of which are coded and quantized into a bit stream for transmission. At a decoder, after decoding and dequantization, the excitation signal and LPC parameters can be obtained to continue LPC synthesis procedure. After the post-processing model, we can get the reproduced output speech. Let's have a summary. LP parameters have some interesting and useful properties that follow from the structure of Levin-Dubin algorithms. The different equivalent representations of LP parameters have different properties under quantization. Polynomial coefficients are bad. Polynomial roots are okay. Polynomial coefficients are good. OSP root angles are good. Almost all the LPC representations can be used in speech compression and are good candidates for the technique of vector quantization. That's all for this chapter. See you next chapter.